Hey guys, welcome to my channel. Now what you're watching at is my first tutorial video about the simulation of hyperelastic O-ring in ANSYS Workbench. Why I made this tutorial is that I have done a project some time ago. I was struggling and stuck in the simulation for a very long time. I hope this video can get you out of the dilemma where I was in. The O-ring is a perfect industrial product, which is simple and useful. It's commonly used in piston seals to prevent fluid bypass between the piston head and cylinder bore while a hydraulic or pneumatic cylinder is operating under various operating conditions. And I am not a native English speaker, by the way, so you may hear a lot of grammar mistakes. Just overlook them. I will do my best to make you guys understand what I want to say. Okay, let's get started. Before we jump into the simulation, let's take a look on the model I used. This model is a joint with male end and female end. The O-ring is placed in the groove. The groove is a narrow cut on the piston. In this case, we will call the radial seal a static piston seal. Under the operation condition, working fluid will go through the joint. What we're going to do is to test the O-ring here can prevent the penetration or not. Well, let's jump into the simulation. And the first step, of course, we have to start the workbench. And from the left side of the screen, we can see the toolbox here. And there are a lot of modules that we can use to analyze different cases. But for today's case, we only need to use the static structure. And we can drag this module into project schematic directly. So the first step, we have to set up the engineering data. Just double click it. And click here to add a new material. We just create a new material. We call it rubber, whatever. And from the toolbox, we can see many options. It's the property of the new material. And under the hyperelastic option, there are several hyperelastic material models like neo-hooking, and the Ogden that we often use. The models are generated from material test data. It depends on what you're going to use. You may be able to find the data in academic books. I usually use EPDM, but today, here I just randomly create a material with neo-hooking model. So I just randomly input the value of shear modulus, 1 million part, and the incompressibility, just changing it 1.5. And now we can see the stress strain diagram is quite reasonable, right? And close it. And next step, we are going to import the geometry. I'm not going to show you how to sketch it because it is based on your design. But it's worth noting that the model is axisymmetric, and two-dimension analysis will dramatically save the computational time. So it is helpful to simplify the model into 3 surface parts on XY plane. And we can rename it. This part to cylinder, and this part for piston, I think. And the circle one is O-ring. And you must make sure that all the parts here are sketched in the positive side of the x-axis. And the figure revolving around the y-axis can produce the 3D model that we want. It means that the distance of this line to the y-axis is the radius of the cylinder bore. And all dimension here of the model is based on the Chinese standard handbook 国标. And you can see the O-ring here has overlap with the piston, which means that the ID of the O-ring is smaller than the diameter of the bottom of the groove. Here I take 0.4 millimeter smaller based on the standard. You can change it based on your design. And also you have better to fill up the corner here and the bottom of the groove to make the computational process easily converge. And I quartered the circle into 4 edges, so I can select 4 edges in the circle part. It's very useful for the later analysis. And that's all for the geometry part. Let's go to next. As I mentioned before, in this case we can use 2D analysis since the model is axisymmetric. So we have to set up the properties. We can display the property window by clicking wheel on the menu bar, properties, and to the properties of geometry. We can switch the analysis type from 3D to 2D. Next, we can go to the matching. It's a good habit to assign the material at first. And the structure still is a default. We just only need to change the O-ring material to the rubber we created before. And the next step is the most important part in the simulation, the contact. There are 2 contact sets. One is the O-ring and the groove, and the other is the O-ring and the cylinder bore. And usually we assign the soft body to contact body. So here, the contact, we choose 4 edges on the O-ring, and the target body, we choose the groove. Okay, next, and obviously the O-ring can slide on the groove and the motion is absolutely frictional, so we change the type to frictional and set up the friction coefficient to 0.1. You can acquire the value from experiment. And behavior, we choose axisymmetric and turn off the trim contact. And for advanced setting, for large diffraction problem, we choose augmented Lagrange formulation. And it's based on pure penalty, but more easily to converge. And detection method on Gauss point. And here we must set up the pinball region and take the radius for 0.3 millimeters so that the region can contain the overlap section here. Now we can see the pinball here. And for the interface treatment, we choose add offset ramp effect. Ramp effect means that the loading can be split in several subsets. And here's the setting for O-ring to piston contact. And now we create a new contact. And we just do the same to O-ring. And the target body is the cylinder bore. Frictional 0.1. Asymmetric, turn off stream contact. Augmented Lagrange formation, Gauss point, and the paintball RAM effect. Okay, that's it. That is the setting for connection. Okay, next, let me show you how to do the mesh. Because it is a 2D model, so the meshing is relatively simple. We just need to do the sizing for the O-ring, select the surface, and element size we choose 0.1 millimeter because the diameter here is 1.8 millimeter for this design. And facing sizing for the piston and cylinder 1 millimeter. And we can do the multi-zone on the O-ring because it has a large diffraction. And method here we choose multi-zone. And three-phase mesh type we choose all quadrilateral. And we can also sizing the contact edge. Just right click, insert sizing, and apply the edge on the cylinder board and the groove. And the size is 0.1 millimeters. And the most important thing, we have to set up the geometry here to the behavior. We have to change it to asymmetric. Now, generate mesh. And the mesh is pretty good here. We can see the quality. Yeah, the quality of the mesh is quite high. It's acceptable. And here's a trick. Right-click model, insert symmetry, and type 2D as a symmetry. 73 repeated. And here is the 3D model. And the next step is the loading part. Before we set the loading, we have to divide the process into 3 steps. And set up the sub-steps. And the first step is the interaction between the O-ring and piston. So we can set up the inertial sub-step 20, and minimum 5, maximum 100. And the second step is the plug-in process. We can make it more larger. And the third process is the fluid penetration test. And the most important thing here is we have to turn on the large diffraction. Okay, now we can set up the loading. The first step, we want to see the O-ring has interaction with the piston. So what we're going to do is just fix the piston. Fix this line of piston. And the second step is the plug-in process. We want the piston can move and plug in the cylinder. But we have fixed it already, so we can only make the cylinder move. So the second step is to insert the displacement for the cylinder. Make it move around the y-axis, so the x component will be 0, and y component will be 5 millimeter is good. But we want to happen after the interaction, so we set it to the second step, because we want that displacement happen after the interaction. So the first step, we don't want to see the displacement, so we can change it to the 0, and the second step is 5 millimeters, and first step 5 millimeter is good. And here we can see the trends. The first step stays still, and the second step it plugs in, and the third step it stays still. And at the first step, we have to apply the pressure rod. It's a little bit more complicated, and in ANSYS, we have to use APDL commands. Here, and we choose the step selection mode to the third step. No, by number, the step number to the third number. It means the last step. And before we coding, we should name the selection of the start point and the pressure path. Here we come to the model. And the start point is the point near the O-ring. So here we choose this point. Right click, create name section. Just name it start point. And next is the pressure path. The pressure path is under the O-ring because the fluid is come through this way. Pressure. Now here we got the name section. So we can go to the APDL command and we coding. The code is complicated. You have to spend some time on it. First, we apply the pressure. And the SFE command means applying 1 million par pressure load on the path. And all set. And next, apply on the start point. So here's the code. It's kind of complicated, but it's short. So I think you can handle it. Now, all setting is done. And the following is post-process. Here we can insert what we want to see, such like total deformation, stress, and most importantly, we want to see the penetration. So here is the contact tool, and insert pressure, contact pressure, and the fluid pressure. And here we just need to click the solve button and wait for the result. Uh-oh, the software engine is unable to converge on the solution for nonlinear problem as constraint. Okay, we have the error here. We can enter the analysis setting to open the nonlinear control, and we can see the Newton Raphson and open it, set it to unsymmetry. Let's see what happens. Okay, the computation is done. And we can see that yes, it's pretty reasonable. In nonlinear problem like that, making it converge is a very difficult thing. So every step, every setting, you should make it adequate step by step. Let me take a look on the pressure. I'll switch it to 2D, it's more obvious. And here we can see as the fluid pressure increases, the O-ring is compressed even tighter into the groove, further increasing the contact pressure. This helps the O-ring seal even better. And we can take a look on the fluid pressure. Blue means there's enough fluid on it, and the red one is the fluid pressure. And here's the fluid pressure from 1 to 1 million pa. And we can see that this part is still 0. It means that there are no penetration happen. It means that the seal is safe and meets our need. From the animation, we can see the interaction between the O-ring and the piston. Next, the O-ring is squeezed by the cylinder. At last, the O-ring is squeezed to the top of the groove by fluid pressure. And no penetration happens, even the pressure is up to 1 million pa. Here are some interesting animations. And that's all for today's video. If you found this tutorial helpful, please give me a thumbs up. And if you have any questions, just comment below or send it to my email. Here is my email address. Thank you for watching. Peace.